So we passed the spec that DOT put forward, and we are using SuperPay specification, so we passed those specification. But then the concern was, can we use in the current construction, which we are using recycled shingle, recycled asphalt, and we always have asphalt present. Are you compatible? And the answer was yes. So we look at the compatibility, phase separation, and so forth. The two materials can be used at the same time. And actually, most asphalt producers that we talk to, they interested to use a blend instead of pure non-petroleum-based adhesive. In a way, they just want to keep the name of adhesive, because our glue, it doesn't call adhesive, it's pie-grade. So we looked at the blend, and we started with the viscosity test to see how these two materials perform and how it affects addition of this different percentage. So with the 10%, for example, here you can see the viscosity of our adhesive, and this is a control asphalt, the first column. The viscosity keeps dropping as you increase the percentage at different temperature, which means it's easier to mix and compact on the road. It's more workable when you have the adhesive, our adhesive in it. We also look at the stiffness properties, and these are at different, as asphalt is a bit viscoelastic material, so it is a time and temperature dependent. So we look at it different time or frequency here, and you can see that stiffness modulus, it keeps dropping. This is the control, and this is our 10% addition of the adhesive, the modulus dropping. We look at M value. This parameter here is basically a measure of how fast the material can release the load. If you imagine if you have a bar or a steel bar or a concrete bar, a material, literally, you cool it down, it shrinks, and if you're confining on the side, you're building a stress within the material. So the only way for the material to release those stress is either crack, which you typically see it on the road because you want to release the stress, so it's crack, or deform. If it is compliant, if it's flexible to deform, it can release the stress without cracking. That's what we want in terms of asphalt, because we want it at the winter time when it shrinks to be able to release those stress without cracking. So the M value, the higher M value for us is better, but basically here the cutoff, the threshold for specification is 0.3. So as far as you're above 0.3, you're good. But let's look at this minus 30 degrees C. At minus 30 degrees C, we have a control here, which is 64. This is the asphalt that we use in North Carolina. Most of the states except New England, Massachusetts area, which are another grade. But when you add 10%, you're actually much better in terms of releasing the stress. So you can, with this material, you cannot build the stress as such. You don't get to the maximum strength of the material, because basically the crack happens when the stress built into the material is more than the strength of the material. If you don't reach to that peak at its strength, it's not going to crack. So we tested almost any cracking test that is available in US and Europe. These are the tests common in US. This one is more common in Europe, so does this one. And of course the numbers are different because the geometry, the mode of loading and so forth is different. We wanted to see if you test it with different tests, if the result is consistent or not. Are we getting improvement with all these tests in different countries and so forth? And the answer was yes. So this is a typical asphalt. This is the modified version. You can see each one of these columns, it has an improvement, different amount, but still improvement. So that was interesting in terms of cracking. So we proved that yes, the cracking resistance at low temperature is improved. And then we started adding more recycled material, recycled shingles, and so forth to see how far we can push the envelope using this material. So for example, this one is the creep compliance curve, and this is with 45% recycled material. That's the curve with adhesive. This is a control. The red is control. Same thing here. The red is control, and this one is our adhesive. So with 15% and 45%, we had very good success by getting the control properties. So basically, you have 45%, but it behaves like there is no recycled material. We also did a lot of fracture tests and tensile characterization. This is the fracture test that we did here. We measured the fracture energy and how much energy it takes to crack this material, and the results were very promising in terms of cracking. This is the energy. You can see here the column for the virgin material, and the green is our adhesive, the red is control. And for 45% wrap, we are still much more above the control one, which means it takes more energy to break the adhesive when we have the bio-adhesive in it compared to the control one. And we also look at the TSR results in terms of the moisture resistance and rotting, and so we have this accelerated testing facility in the lab that runs 20,000 pass to kind of simulate long-term performance. We don't have an actual field section yet, but these are basically the tests that is required by the Department of Transportation. So you may say that this whole thing is even possible getting from pigment ore to an adhesive that works like that. Well, I'll let Mahour give you some facts of how we got here.